So we know that future value can be calculated using this formula. We also know that for just simple compound interest, we have this formula. And so what we're going to do is we're going to now redefine A. A is our future amount. So A is going to be future value. And P here, that principal amount at the start, that's going to be known as present value of the annuity. And what this formula then becomes is that the future value is going to be equal to the present value multiplied by 1 plus r over n to the power of nt. Okay, so fine. What can we do with this though? Well, we can actually now look for a formula involving present value. So if I just take this and solve for present value, we get present value is equal to future value multiplied by 1 plus r over n to the power of negative nt. Okay, if I were to bring this over to the other side, it becomes negative nt. Okay, fine. Except that we also have this formula up here that we can use to replace future value by. So that means that present value is going to be equal to PMT, okay, and I'm just taking that from up here, multiplied by 1 plus r over n to the nt minus 1 over r over n. And now I'm going to bring this in. So it's going to be multiplied by 1 plus r over n. And let's fix that r over n to the power of negative nt. Okay, so all that we did here was take this future value and this future value and sort of swap that big formula in for future value. So now we want to clean this up a little bit, and specifically we're going to take this term and I'm going to multiply it in onto both of these terms. Okay, and that means that our present value formula is going to become PMT multiplied by, well, if I multiply it on this term, the exponents are going to cancel each other out and I will just end up with 1. If I multiply it on this term, all I get is negative 1 plus r over n to the power of negative nt, and my denominator does not change at all. We still have r divided by n, and so this is the formula that we end up with for present value. We're going to leave it in this format, but if we need to work with present value, this is the formula that we can use. Okay, and it is fairly similar to our future value formula. Okay, it's just as ugly, it's just as complicated, except that for this one, this is what we can use to find the present value of an annuity. Now, we know for an annuity what the future value represents. It's the amount that you're going to have in the account, for example, after T years. We also know that we can think about present value as sort of the amount of money that you would need at the start to just leave and accrue interest over those years to have the same future value at the end. But there is another way we can also think of present value. Okay, and what we're going to look at next is called a payout annuity. All right, and a payout annuity is going to work primarily with present value. So right off the bat, for a payout annuity, what I want you to think about is just something like a retirement fund. Okay, so you put all this money in over the years, but at the end you're going to be taking money out of the retirement fund to pay yourself to live off of. So this is going to be called a payout annuity. Okay, and a payout annuity is one in which the balance of the account is reduced by a fixed amount at regular intervals. Okay, so whatever you have in your retirement fund, it's going to be getting reduced every month as you take money out, for example. And in a payout annuity, what you're looking at is present value, and here present value will be the initial amount in the actual payout annuity. And if that is your present value, then we can use our present value formula. Here, PMT is going to be the amount that you are actually withdrawing from the account. okay, every month, every week, whatever the case is. It's the amount of your withdrawal. And otherwise, the formula remains exactly the same as what we saw before. And this is how we can work with payout annuities. So make sure that you understand how it's related to present value. And also here we have that PMT is the amount of the payout. So now we know how to deal with basic annuities and we know how to deal with payout annuities. We have all our formulas. We're going to actually go and do one example, okay, looking at sort of all of this linked together. So here to start off, we're looking at a situation where you deposit $100 every month into a retirement account, and your retirement account is earning 6% annual interest compounded monthly. Okay, so once again, you'll notice your deposits are going in every month. The interest is being compounded every month. For all the examples that we do, that's going to be the case. And the question is this: how much are you going to have after 20 years? So fine. What we end up getting is that we are looking here to find the future value. Okay, what is going to be the future value of that annuity? We are given the amount of the payment. The payment amount will be $100. We also know the interest rate is 0.06. We have N. N is the number of compounding periods per year. For us, that's going to be monthly, so N is 12. And T is the number of the number of years that we're looking at. T is going to be 20. And so we can go and use our future value formula. Future value is the amount of our payment multiplied by 1 plus R over N to the NT minus 1 over R over N. And we plug everything in here. Our payment amount, we have 1 plus 0.06 over 12 to the 12 times 20 minus 1 over 0.06 over 12. Okay, and so you don't have a choice. You do need to get out your calculator for this. But again, pause the video, get out your calculator, make sure that you can reliably do these calculations. Let's see what we end up with. What you should end up with is $46,204.09, and that is the amount that you would have in your retirement fund after your 20 years. Okay, so now we're going to switch it up a little bit. We're going to sort of extend this question a little bit, and we're now asking ourselves this question. Okay, we know that we would have $46,000 if we put $100 in every month. But what if instead our goal was to have $100,000 after 20 years? Okay, if you wanted to have $100,000 after 20 years, how much should you be depositing every month? So in this case, we now know that the future value is $100,000. And here it's actually the payment amount that we're trying to find. That's the unknown. Everything else, though, still stays the same. We have R is 6%. We have N is 12. Because it's compounded monthly, and we have T is still going to be 20 years. Okay, so now we want to plug all of this in using the same formula. So we have 100,000 on the left, that's our future value. The payment amount is what we don't know. And on the right, we're going to have 1 plus R over N to the power of NT minus 1 divided by R over N, so that's going to be here 0.06 over 12. And here again we're trying to solve for the payment amount, so you end up getting 100,000 is equal to the payment amount multiplied by all of this. If you plug that into your calculator, you're going to get 462.04. So you end up getting your payment amount is going to be $216.43. So that's the amount that you would have to deposit every month if your goal was to have a future value of $100,000 after 20 years. Okay, so again, we've sort of looked at this future value now in two different ways. Once where we wanted to find the future value and once where we wanted to find the payment. Okay, but now let's take a look at a slightly different sort of question. Okay, if we're still considering a retirement fund, what if you wanted to retire in a certain way? Okay, so if you plan on retiring and you would like to be able to withdraw $750 a month from the account during your retirement, okay, how many years will this fund last? So if you have $100,000, okay, and you want to be able to withdraw a certain amount every month, then that's going to be looking at a present value problem. The present value is our $100,000. The payment amount, or in this case, the amount that we would like to withdraw every month, is $750. And the interest rate is going to remain the same. So if that money still stays in the account, the money that's still in the account is going to be earning 6% interest the whole time. N is 12 because it's still being compounded monthly. And for this one, we want to know how long is that money going to last? How many years will you be able to continue making these withdrawals? So now we're using a present value formula. We have our payment, and we have 1 minus 1 plus r over n to the negative nt divided by r over n. And here we can plug everything in. We know that our present value is 100,000. The amount that we want to be able to withdraw is 750. We have r is 0.06, n is 12, and the only thing we don't know is t. Now, unfortunately, not knowing t here is going to make this just algebraically a little bit more difficult for sure. Okay, you'll notice that t, which we're trying to solve for, is right here in the exponent. So that means we're going to need to use a logarithm at some point to get it out. But until that point, we're just going to sort of work on simplifying the algebra that we have here. So first off, let's bring this over to the left-hand side. So we're going to multiply both sides by 0.06 divided by 12. And that means that on the left-hand side, we have 100,000 multiplied by 0.06 over 12. And then at the same time, let's divide by 750. Okay, so we're going to divide it by 750, and that leaves us on the right-hand side with 1 minus 1 plus 0.06 over 12 to the negative 12t. Okay, so let's work with this. If you simplify the left-hand side, it actually works out rather nicely. You end up getting just 2/3 on the left is equal to 1 minus 1 plus 0.06 over 12 to the negative 12t. And that means that here, if I bring maybe this over to the left so that it becomes positive and my 2/3 over to the right, we end up with 1 plus 0.06 over 12 to the negative 12t is equal to 1 minus 2/3. And 1 minus 2/3 is just going to be 1/3. Okay? Now, we need to get this t out of the exponent, so this is where we're going to now take a logarithm. And we're going to take a logarithm of both sides. Okay, so we're going to get ln of the left-hand side is equal to ln of the right-hand side. Now, let's sort of write that out on its own. What we end up with is ln of 1 plus 0.06 over 12 to the negative 12t is equal to here ln of 1/3. Now, why did we do that? Well, properties of logarithms means that we can now take this exponent out of the logarithm, and we end up getting that negative 12t is going to be ln of 1/3 divided by ln of 1 plus 0.06 over 12, and then I can plug all of this into my calculator, divide it by -12, and you should get your value of t. So again, make sure you're comfortable with your logarithms for this. You should end up getting that t is equal to 18.36 years. Okay, and so that is the number of years that you would be able to consistently withdraw your $750 every month from your retirement fund. But unfortunately, after that much time, your retirement fund would be empty. Okay, so that's sort of the idea, guys, with annuities. Okay, we've looked at them as sort of an investment or a savings account. You're putting money into it on a regular period of time, and then we've also looked at it as a sinking value, a decreasing value, where you have your present value is the amount that you start with, and you are decreasing that by a set amount every period. Okay.